Hey everybody, Mr. Brooks here again. So today we are going to go over section 11.9, which is representations of functions as power series. So in this section we're going to find out how to represent certain functions as sums of power series. Here we're going to use geometric series and by differentiation or integration. So we'll talk about that more. This is again beneficial later on when dealing with functions that have no what we call elementary antiderivatives and solving differential equations and approximations. So first of all, let's consider the following. Okay, f of x is equal to 1 over 1 minus x. Well, what does this look like? This looks like the sum of a geometric series. All right, because think about it. Sum of the series is n goes from 0 to infinity of ar to the n was equal to a over 1 minus r. So notice this would look like, hey, that a is 1 and r is x. And in fact, if a is equal to 1 and r is equal to x, now again, r is some number here, so x is going to be a fixed value, we get sum of the series is n goes from 0 to infinity of x to the n, which is equal to 1 plus x squared plus x cubed and so forth. Which is equal to, if this, okay, again, be careful here, is equal to 1 over 1 minus x when the absolute value of x is less than 1. Okay, so this is the idea here. We're going to look and see if we can make a function if it has this base idea of like this 1 over 1 minus x, if there's some form of it. So this is why we say integration and differentiation might be one of our uses that pops up out of this. Okay, so that's all we've done. So here, this has actually been our very first thing. This is a function. This is a power series. So this is our power series representation of the function 1 over 1 minus x. So we have already done it. So we're done with the section. Yay! There's more. That was only 3 minutes of lecture. So you got to know that there's more than this. All right. So let's go to the next thing. Express f of x is equal to 1 over 1 plus x squared as the sum of a power series and find its interval of convergence. Okay, so what do we need? Well, we need 1 over 1 plus x squared to be in the form of a over 1 minus r. So we need that to occur. All right, so let's see. Can we rewrite this? Can we find our, what we're doing here is we're seeing if we can find our a and r, really is what we're trying to do. So let's look at this. Well, I need negative in here. I need a negative to occur. Well, one way to do that is 1 over 1 plus x squared. We can rewrite this as 1 over 1 minus, well, if I pull a negative out here, it means I need a negative to come back, x squared. Now notice here, this is distributing to the negative, so that's going to be positive. So it's not negative x to the second power, it's negative x squared. So notice parentheses are very important. Well, that's all I need. So now I just replace back with our geometric series. Here a is equal to 1. R is this negative x squared. So this would equal, again, if we converge, as n goes from 0 to infinity, of negative x squared all raised to the n. Well, another way to write that is as an alternating series. Negative 1 to the n, x to the 2n. All right, so this is our power series representation of 1 over 1 plus x squared. And we could rewrite this series out now as 1 minus x squared plus x to the 4th minus x to the 6th plus so on. All right, again, provided that this converges. So this is why I said find its interval of convergence, because this is only true where this converges. For what values of x does this converge? So since this is a geometric series, we get to use some properties for us. It converges when the absolute value of negative x squared, so this is our r, is less than 1. So that is to say, x squared is less than 1, or another way to state that is the absolute value of x is less than 1. All right, so the interval of convergence, which we talked about in 11.8, is -1 to 1. So therefore, the powers representation of 1 over 1 plus x squared is equal to this -1 to the n x to the 2n. This is only true for values of x between -1 and 1. Okay, and that's it. That's all we're doing here. Okay, so there's not really much trickery that's going on here. It's just realizing some relationships between geometric series and functions. In fact, the sum of a geometric series. So that's where we're going for. All right, so let's up the ante just a little bit. Find the power series representation for f of x is equal to 1 over x plus 2. All right, again, we need to get that format. So I like stating this, so if you want to pause the video, you can go ahead and do that. All right, so we need 1 over x plus 2 to be in the form of 1 over 1 minus r. So if we can get that, we're great. All right, so here's our solution. I'm going to rewrite this just slightly. This is why I'm using green here to show the difference. All right, I need this to be 1 minus r in the denominator. Well, the only way to do that is I need a 1 here. Well, I could pull out a 2, and then I'm left with 1 plus x over 2 when I factor a 2 out from both of those. All right, so I'm getting close. I need this to be a minus. So I'm going to get 1 over 2 times 1 minus negative x over 2. So a way to write this in this format is 1/2 times 1 over 1 minus negative x over 2. So this is just going to get algebraically intense is what's going to happen. So again, not trying to trick you, this is what's going to happen. So this is equal to 1/2 times the sum of the series as n goes from 0 to infinity of our r, negative x over 2, all raised to the n. Now, I want to stop here for just a second and tell you what to look for. If we're talking about where a series converges, it's best to look at this as is right now before you simplify down, because this is going to help you determine what your interval of convergence is going to be. Okay, because we have this isolated. We want negative x over 2, the absolute value of it, to be less than 1. So that's what we're going to get to. So another way to write this more simplified, however, is I can bring that 1/2 in, and then I could say -1 over 2 to the n, because that's the coefficient here, x to the n, which then we can rewrite again, just a little bit more simplified, as -1 to the n plus 1, to the n, all divided by 2 to the n plus 1, because we actually have an extra copy of 2, x to the n. So this is just a simplified version as we go through. Now again, to focus on the interval of convergence, the series, again because it's geometric, converges when the absolute value of negative x over 2 is less than 1. Or, by rewriting this, absolute value of x is less than 2. The interval of convergence is -2 to 2. Again, remember when we talked about interval of convergence and radius of convergence, we talked about the format of x minus a is less than r. I need that leading coefficient of x to be 1. So in order to do that, I multiply both sides by 2. The absolute value got rid of the negative, and so this is why we have the interval of convergence is -2 to 2. Okay, and that's it. That's what we're doing for this. So the next examples are, we do have a theorem that comes out of this that's just going to be really handy. But the next examples that we go through are dealing with just a little bit more complicated pieces. All right, so the first one we're going to look at here that's a little bit more complicated is x cubed over x plus 2. Note this is very similar to the one that we just looked at. Okay, the only difference here is that we've multiplied it by x cubed. So let's see what happens. All right, so again, an important note that I'm going to be incorporating here, so make sure that you follow this. Note that this is just our previous example multiplied by x cubed. So we have x cubed over x plus 2, which means we can write this as x cubed. Now again, think about x. X is a fixed value. So in the grand scheme of things, this is a constant value. Okay? Multiplied by 1 over x plus 2. We've already found its representation in the previous problem, which was the sum as n goes from 0 to infinity of -1 to the n over 2 to the n plus 1 x to the n. And now we bring in this cubed part, so n goes from 0 to infinity, -1 to the n over 2 to the n plus 1 x to the n plus 3. And that's it. And so these would look like 1/2 x cubed minus 1/4 x to the 4th plus 1/8 x to the 5th minus so on. So this is what this would look like. And just like before, again, I'm multiplying by a constant value, so that is not going to affect my interval of convergence for that with this x. Okay, so x is still having to be the absolute value of -x over 2 has to be less than 1, and so absolute value of x has to be equal to 2, or less than 2. So just like before, the interval of convergence is -2 to 2. And again, you can verify this. So if you want a little bit of extra practice, you can verify this using geometric series properties or the ratio test. And you'll get the same result. So that's the cool thing with this one. All right. So moving on. The sum of a power series. So again, think about what we talked about in the previous section, 11.8. The sum of a power series, again, the summation, as n goes from 0 to infinity, of c sub n, x minus a to the n, is a function whose domain is the interval of convergence. Okay? So why I'm recalling this is if we know a function is defined on a certain interval, that means we're able to differentiate it on that interval, provided that there's no sharp points and everything like that. Well, think about this. We're dealing with polynomials in a sense, right? So we should be able to use differentiation or to differentiate or integrate just like a polynomial. Because think about the sum of that series. All right, let's scroll back up here, see if I can find it. All right, so we have this sum here of the series that's a function, provided that this converges. Well, we can integrate term by term and differentiate term by term. So that's where our next theorem is coming into play. So this is what we're pushing for because we're going to need this later on. So if a power series, we'll use blue, again, showing the format, and we've seen this index change, so that's okay. If the power series has a radius of convergence of r is greater than 0, then f of x is equal to c sub 0 plus c1 x minus a plus c2 x minus a squared plus so on is equal to, as n goes from 0 to infinity, of c sub n x minus a to the n. So this function is differentiable. All right. On, and another way to write that is continuous. So differentiability implies continuity, but continuity does not imply differentiability. So if it's differentiable, then it's continuous on a minus r to a plus r. And this is the cool part. Number one, f prime of x is equal to c1 plus 2c2 x minus a plus so on. Again, just taking the derivative term by term. So the next one would be 3c3 times x minus a to the second. This is equal to, n goes from 1, notice the change, when we take the derivative of the series, it's going to change the index of n, c sub n, x minus a to the n minus 1. So let's just double check that. If I plug in n is equal to 1, I'm going to get a 1 here. I'm going to get c sub 1, x minus a to the 1 minus 1, which is 0, so this is going to go to 1. So notice I get this first term here. And if I plug in 2, I'm going to get 2c2, x minus a to the first. So notice I get that. And notice what that looks like. This is taking the derivative of that formula. I bring that n out in front. X is what we're differentiating by. And so we take 1 away from the index, or from the power. Number 2, the integral of f of x dx is equal to our constant of integration, big C, plus c sub 0, x minus a, plus c1, x minus a, the quantity squared, divided by 2, plus c sub 2, x minus a, cubed over 3, plus so on. This is equal to big C, constant of integration, plus the series as n goes from 0 to infinity of c sub n times x minus a to the n plus 1, all divided by n plus 1. And let me write that in a different color because it's blending in. Zero to infinity, c sub n, x minus a to the n plus 1 divided by n plus 1. Notice what this does. I've integrated this series formula of x minus a to the n. I add 1 to the exponent, divide by the new exponent. C sub n, these are constant multiples, or scalar multiples, if you will, so those guys are unaffected, so we only integrate with respect to x, and we have our constant of integration. All right, here's the really cool part. The radius of convergence in both 1 and 2 are both r. So it's unchanged. The important note here, though, that we need to make is though, we'll do this in green, though the radius of convergence, ROC, is unchanged, the interval of convergence could change when integrated or differentiated, because we are changing the parameters of the problem in that case. So that's one thing to be careful of. But that's a good thing, is we already have our potential interval of convergence. The only thing you have to do is check the endpoints. So that's not a horrible thing to do, because then you're only checking two things and you're done. So nothing bad. So again, if you take the derivative or the antiderivative, the radius of convergence stays the same. The interval of convergence could change. So it could be the same, or it could be that we have inclusion on the endpoints, or one of the endpoints is included but not the other, or it's equal to the original. So there's three different options that occur with that. Well, technically four if you talk about left endpoint versus right endpoint, but either one of the endpoints could change its convergence or divergence property on that part. All right, so let's look at something where we have to apply this theorem. All right, it doesn't look like that we have to on this one, but take a second and work this guy out. All right, express 1 over x plus, or sorry, 1 over 1 minus x, the quantity squared, as a power series by differentiating 1 over 1 minus x. So here I'm actually giving you what we need to do. And the reason that we're doing that is we can't rewrite this as 1 over 1 minus x, or in that format of 1 minus r. So what we're going to use is differentiate. Well, what happens when I differentiate a fraction? I square the denominator, and then I deal with low d high minus high d low, right? Or bottom times the derivative of the top minus top times the derivative of the bottom. So using the quotient rule. But the key here is this x squared, or this quantity squared, and that's what's going to happen when I differentiate. All right, so I'm going to take the derivative of 1 over 1 minus x. All right, so what I want you to see here is 1 over 1 minus x is the same as this series here. So we're going to see this happen. All right, so I am going to get the bottom squared. All right, and then bottom times the derivative of the top, that's 0, minus top times the derivative of the bottom, which is negative 1. So we get positive 1 over 1 minus x, the quantity squared. So notice differentiation helped us there. Well, if we differentiate these terms, term by term, we're going to get 0 plus 1 plus 2x plus 3x squared plus so on. All right, and again, I'm starting at 0 here, so I need to make sure that that's a correct statement. Well, if I do that, shifting this just a little bit, I get 1 plus 2x plus 3x squared plus so on. So my first term has to be 1, the next term has to be 2x, and so forth. Notice if I take the derivative here, I get n x to the n minus 1, which we can rewrite because Think about the sum of a series, of a geometric series. We have it in its proper format. Another way to write this is if I add one to my index, or take away one, I add one on the inside. So this is n plus 1 x to the n. Okay, that's just properties of indices here. Again, if you take away from the index, then you add on the formula. If you add to the index, you're going to take away from here. So if we started at, this is 2, we'd have n minus 1 x to the n minus 2. And then everything would start at the right part. Here, notice that it's x to the n. So our radius of convergence is still equal to 1. So that's the cool thing. All right, that's all this is. So let's go over a couple more examples. All right, find the power series representation of natural log of 1 plus x and its radius of convergence. All right, this one's different from the previous one because here in this one I took the derivative of the series. Okay, when I take the derivative of the series, notice that the index changed. Now, here I need to take the derivative first because it's not in our format of 1 over 1 minus r. So this is the big difference, so be careful on that. So let's take the derivative of the natural log of 1 plus x. Okay, well this is equal to 1 over 1 plus x. So now I can rewrite this. This is going to become 1 over 1 minus negative x. So this is the series as n goes from 0 to infinity of negative x to the n. So it's an alternating series. Okay, so this is going to look like 1 minus x plus x squared minus x cubed plus so on. And this is true when absolute value of x is less than 1. Again, radius convergence because this is a geometric series. If we wanted to go one step past this, the negative gets absorbed into the absolute value, and so this is what we're going to get. All right. Okay, so this is the series representation of 1 over 1 plus x. Next, I need to get back to my natural log. Well, the natural log of 1 plus x is equal to the integral of its derivative, right? So let's write that. So we're undoing our derivative. Well, we found out the derivative is the integral of 1 over 1 plus x dx. So we already know that. And its power series representation is 1 minus x plus x squared over, plus x squared minus x cubed plus so on dx. All right. This is equal to taking term by term integration, x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, so on, plus our constant of integration, which is equal to the series as n goes from 0 to infinity of negative 1 to the n. This gives us my alternating piece, so notice it starts at 0, so it's positive, negative, positive, of x to the n over n. Now we do have to be careful, this is going to start at 1. So that's one thing we do have to be careful about. Plus c. And then that's all we need. Right? So, and again, if we took the derivative of this, integrated, we would get, and we do have to be careful, we do have to shift some things around, and negative 1 to the n, x to the n. So if we integrated that, notice that we get x to the n plus 1 So the negative 1 to the n comes around. Forgot my infinity symbol. All right. So if we integrate it, and then we get x to the n plus 1 divided by n plus 1 plus big C. So there's a couple ways that we could represent that. So notice that the index does not change. Here I'm starting at 1. Down here I'm going to circle this in red. Okay. Actually, do that real quick. All right. And so notice it starts at 1, but if you look at the index, there's an agreement in the terms. So n starts at 1. We get 1 in the denominator. We get 1 in the denominator with 0 here. And then we get x to the first. So notice that there is an agreement in the terms for these guys. So this is why we're starting at 1, because we have x to the n. This is just to get into that representation for that piece. All right. So let's look at arctangent. But before we do that, there's one more thing I want to point out. Is if we want to find out what C is, notice that 0 is the center of our, when it's written in this format, our center, the center, A is equal to 0. Okay? And so what we could do is we say, we'll take the natural log of 1 plus 0 and set it equal to this. Well, if I plug 0 into here, this guy goes to 0, and we're left with C. So in this case, this implies that C has to also equal 0. Therefore, and I'm going to talk about this again just in a second, the natural log of 1 plus x is equal to, series as n goes from 1 to infinity, of negative 1 to the n minus 1. Oh, and I need to change that. Minus 1 here. Because notice that we have to start with a positive here. Negative 1 to the n minus 1. X to the n over n. And again, our radius of convergence is 1. Okay, so again, where I'm going with that, just to make sure that everybody's following, is I want to find out what C is. Sometimes I don't ask you that, so sometimes you'll have to find C, sometimes you won't. But notice here that the center, the way we have set this up, the center is equal to 0. All right. And so since the center is equal to 0, I can plug in 0 because this is convergent at its center. When plugging 0 in for x, I'm going to get the natural log of 1 plus 0 is equal to just C because all of this goes to 0. And so that implies C is equal to 0. So therefore, this is our power series representation of the natural log of 1 plus x. All right. And again, make sure you make this correction that this is n minus 1, just to make sure that it's starting at a positive term and then goes to a negative. All right. So let's look at arctangent real quick. So find the power series of representation of arctangent. Well, we know the derivative of arctangent is equal to 1 over 1 plus x squared, which we can rewrite as 1 over 1 minus negative x, the quantity, or negative x squared, which then we can rewrite its power series representation as n goes from 0 to infinity of negative 1 to the n, x to the 2n. Okay, and again it starts 1 negative x squared plus x to the 4th minus x to the 6th, and so on. All right. So here, just talking about what's going on, again, just rewrote the derivative as a power series representation. and then wrote out the terms. Again, since we have x squared, we know the radius of convergence for this guy is x squared is less than 1, or another way that's stated is that x is less than 1. So its radius of convergence is still 1, center is 0. Okay, so just stating that. All right. Now, well, we're going to integrate. Arctangent of x is equal to the integral of 1 over 1 plus x squared dx, which is the same as if I took the integral of all these terms of 1 minus x squared plus x to the 4th minus x to the 6th plus so on. Okay? Well, this is going to give us constant of integration plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. Well, I'm going to take a second real quick. I want to find out what this constant of integration is. So if we let x equal a, its center, again, center, we can find out what this value is. Because arctangent of 0 is equal to, and if we look at these terms, if I plug in 0, everything goes away except for c. All right? Well, arctangent of 0 is 0, so c has to equal 0. Thus, arctangent of x is equal to the series of just x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus so on, which its series representation is going to equal, as n goes from 0 to infinity, of negative 1 to the n, so we're starting out positive, and then we're going to have x to the 2n plus 1 all divided by 2n plus 1. And again, if we integrated this series, look what happens. We get x to the 2n plus 1 divided by 2n plus 1. All right? And again, its radius of convergence is 1. All righty. So another thing that we can do with these is so notice that there are some things that we can't integrate. We've talked about that before. So we can use this to use approximations, just like what we did in alternating series. So that's actually going to pop up here in just a second. So let's evaluate 1 over 1 plus x to the 7th as a power series, then use this to estimate our integral, the following integral, from 0 to 0.5 of 1 over 1 plus x to the 7th dx. All right, to within 10 to the negative 7th. Okay, so first of all, let's find the power series representation of the integral of 1 plus 1 over x to the 7th. All right, so we have 1 over 1 plus x to the 7th. So a way to write this is 1 over 1 minus x, 1 minus negative x to the 7th. So this is our r. This is equal to, let's integrate this guy. Yeah, let's not throw that in yet. Let's just leave that alone. This is equal to the series as n goes from 0 to infinity of negative 1 to the n, x to the 7n. And again, radius of convergence is equal to 1. Because we have the absolute value of x to the 7th is less than 1. So absolute value of x is less than 1. So we're still good. All right, so now we're going to integrate 1 over 1 plus x to the 7th. So that means we're going to integrate its power series representation. All right. So when we do that, everything else is treated as a constant. Again, term by term is what's happening. So we're going to get -1 to the n because this is integrating with respect to x. So anything that doesn't have an x involved with it is a constant multiple. So that means we're going to get x to the 7n plus 1 divided by 7n plus 1 plus our constant of integration. So this is the power series representation of the integral of 1 over 1 plus x to the 7th. All right. So looking at this, our terms are c plus x minus x to the 8th over 8 plus x to the 15th over 15 minus x to the 22nd divided by 22 plus x to the 29th over 29 and so forth. Or minus sign in there. All right. Well, we know this guy converges on the interval from -1 to 1. So that means we can integrate if we're within inside that interval. So one important note I want to make here, the fundamental theorem of calculus, which we haven't talked about in a while, so the FTC, it doesn't matter so according to the FTC, it does not matter which antiderivative we use. So we're going to let c equal 0. Again, because those constants of integration would cancel each other out when we're doing the evaluation part. So c is going to be not needed in this case. So there's some nice things with that. So let's look at this. So if I take the integral from 0 to 0.5 of 1 over 1 plus x to the 7th dx, this is equal to its antiderivative, and I'm writing out the power series of x minus x to the 8th over 8 plus x to the 15th over 15 minus x to the 22nd over 22 plus x to the 29th over 29 and so forth. Evaluated from 0 to 1/2. Okay. Well, this is equal to, when I plug 1/2 in, because if I plug in 0, everything goes to 0, I'm going to get 1/2 minus, and I plug in 1/2, I'm going to get 1 over 8 times 2 to the 8th plus 1 over 15 times 2 to the 15th minus 1 over 22 times 2 to the 22nd plus 1 over 29 times 2 to the 29th and so forth. All right. So if we looked at this, this is the same thing as saying that the series goes from n is equal to 0 to infinity of -1 to the 1 over 7n plus 1 times 2 to the n, 7n plus 1. Again, plugging in, if we look back here, if I plugged 1/2 in for x, that's the same exact thing. Notice that this is an alternating series. All right, and in fact, since this is an alternating series, we know this also converges, that is convergent from -1 to 1. Because again, and I don't care about the endpoints because I'm only evaluating from 0 to 1/2, so I'm inside this interval. I'm not going to the endpoints. And again, the reason for that is because previously we said that the radius of convergence of this guy was equal to 1. And we set it up as x is less than 1 for that case. So since I know this is a convergent alternating series, I can apply, or we can apply, the alternating series estimation theorem. So notice why I'm saying that we can use approximations here. All right, which states that the remainder is equal to s minus s of n is less than or equal to b sub n plus 1. We want this to be less than within 10 to the negative 7th, okay, which is equal to 1 over the bunch of zeros. All right. So that's the cool thing. So all we really have to do is start seeing when the 7th decimal point is being affected. Okay. So let's look at the values. So when n is equal to 2, so the first one is 1/2. So let's look at this value. This value, if it is less than 10 to the negative 7th, we're good. All right. Well, the nth term, the b sub 2 term, is equal to 1 over, sorry, this term is 15 times 2 to the 15th, which is approximately equal to 2.03 times 10 to the negative 6th. All right, so this is not small enough. It is not smaller than 10 to the negative 7th. So let's look at the next term. N is equal to 3. All right, and the reason I'm doing this is because this is 0 term. This is the first, second term. Third term, we're going to look at 1 over 22 times 2 to the 22nd. All right, this is approximately equal to 1.08 times 10 to the negative 8th. The issue is this has an effect on the 7th decimal place. So there's an issue. So let's go one step further. If we look at the 4th term, or the n is equal to 4 term, we get 1 over 29 times 2 to the 29th, which is approximately equal to 6.4 times 10 to the negative 11th. This does not affect our 7th decimal place and is smaller than our error. Of 10 to the negative 7th. All right, so a way to write this up is if we stop adding after the 3rd term, sorry, the n is equal to 3 term, so it's the 4th term, since we're starting at n is equal to 0, the error is smaller than the n is equal to 4 term. So the integral from 0 to 1/2 of 1 over 1 plus x to the 7th dx is approximately equal to 1/2 minus 1 over 8 times 2 to the 8th plus 1 over 15 times 2 to the 15th minus 1 over 22 times 2 to the 22nd, which is equal to 0.49951374. So this is the n is equal to 0 term, n is equal to 1, n is equal to 2, and n is equal to 3. So this is how we can use this to approximate integrals, because there is no way that we could have figured out the integral of 1 over 1 plus x to the 7th. That's the cool thing, is we can use series to approximate integration, which is awesome. That's why this set of sections is highly important because of the things that we do not know how to do. Has a basic elementary antiderivative, then we can use series representation to approximate and approximate to very high levels as well, provided that we do have convergent series and all of that. The next thing that we're going to do is, well, what if they don't have this nice format of 1 over 1 minus to the, or 1 minus r, like what we've dealt with arctangent, natural log, and the what we've seen so far. Those guys have been pretty straightforward. We either had to use a derivative or an antiderivative or as is, and just do a simple rewrite to get it into that format. Well, sine and cosine don't have that. E to the x does not have that derivative or antiderivative of 1 over 1 minus some value. So what do? Well, that's where Taylor series is going to be coming into play. So this is where section 11.10 and 11.11 are going to be highly important, is because we're going to find if they do have a power series representation, then this is what it looks like. And then we're going to prove on a couple of them if it does have a power series representation or not. So this one, we're guaranteed that they have power series representations that are of the geometric form. And in the next section, we're going to see those that do not. And so that's where we're heading to for the next section. All right, you guys have a wonderful day, and I'll see you in the next lecture.